also need, so then, you also show you, Number 16, number 17 about the merge sort, right? Yeah, about merge sort. Yeah. So here, number 16, I ask you to do the merge sort with 8 elements, but for the best case. Yeah. The next question for 12 elements for the worst case. Yeah. But those students, some students, they try to find some formula. So here, I ask you, work it out, okay? Write all the details, your solution details, step by step, divide and conquer. Yeah. So use the diagram I show you in our notes. In the notes, I drew a diagram, right? It's split in the middle, merge. Yeah, but here we need to do the details step by step. Yeah. Here, let me show you. Okay, so here I use 2 concrete examples to show you what I expect you to do. Okay, what's the right way to do? Some students just find n log n and plug in numbers. Don't do it. Okay, do not use that n log n. N log n asymptotic notation. That's for the case n is very large. Here our n small. N equals 8, n equals 12 small. So when n is relatively small, asymptotic notation does not work. Okay? Asymptotic notation is not for the small n number, for big n numbers. All right, yeah, so let me show you how to do the details. But here, when I show you, I use different numbers. Yeah, so 8, that's your original question. Here, I just use 10. How about that? So there are 10 elements. Let us do the merge sort for the best case. Then the next slide, I do the merge sort for the worst case. Yeah. Just we need to change a different formula. Yeah. All right, first, the best case, we know when we merge 2 arrays for the best case, minimum of m and n for the best case formula, okay? So worst case, m plus n minus 1. So each step, every time when we merge 2 arrays, we apply this formula. That's the best case, okay? Yeah. All right, but in order to make our discussion a little easier, the meaning easier, here I need to use a notation. I need to choose a notation. Okay? Yeah, otherwise, I need to write a lot of sentences. Yeah, so here I do not write many sentences. I just use special notations. So here, this notation I like to use in my work. Okay, all right. Because when we do comparisons to merge 2 arrays, all right? Yeah. So here, this notation for a merge result. After we do a merge, we need to represent the result. So I use this notation. So what's that? The merge result. I use parentheses A bar B, separate. This notation means that we use A comparisons to merge the 2 arrays. Excuse me. then B, and the merged array has B elements. Because after the merge, the number elements after the merge, we need to use that number. Right? So that's why this notation, we need these two numbers. First, comparison number, but that's not enough. We need a second number, the array size. After the merge, what is the size of the array? After the merge, okay? Size of the array after the merge. That number is useful, so we use B to store it. Okay? Yeah. All right, so after this assumption, now let's do the work. Okay? Let's do the, 10-element array merge sort. Yeah. Yeah. All right. First, I split because of the 10 elements. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So when we do the split, so we use the median, to give us the line, okay? The boundary for the split. The first split here, okay? So the first split here. Yeah. So 5 elements, divide and conquer, divide. Okay. Second split, 3, right? Yeah. So here, second split. Second split, okay? All right. Here, second round, all right? Yeah, second round. Then third round, here, third round, all right? Third round, all right? Third round, all right? Third round, all right? Then fourth round, although we can, because here 1, 2, we can split another time, fourth round. Yeah, but here I like to modify. Yeah, because the last round, fourth round is the last round, right? Last round here, I want to simplify a little bit because last round only 2 elements. 2 elements, we just do one comparison. We sort it, right? Yeah. So let's save that split. Let's just do one comparison. Get a full bottom level, sorted. Yeah. Small improvement. Okay, small improvement. Yeah. All right. So here, let's count. I need to use different notations. One comparison here. Okay. Yeah. One comparison. When you see 2 elements, one comparison here. All right. So no further split, all right. So here, this round, we need to, 2 comparisons. Okay. The lowest, you can call the fourth round. Okay. Fourth round, 2 comparisons. Yeah. All right. Then we start merging. Okay, after that, all right? All right. All right, yeah. Because the merge, when we merge, we go the opposite way, 3, 2, 1. So when we merge, when merge, we go opposite way. What do you mean opposite way? So we inverse 3, 2, and 1. Okay? Yeah. Yeah. Round 3, reverse round 3, round 2, and the round 1. Okay? So that opposite merge. Okay. All right. So 3. Yeah. So the 3 combine merge these two subarrays, right? Yeah. So you do the merge with respect to the dotted line 3. Okay? Dotted line 3. You do merge. Okay. All right. Yeah. When you do merge, m, yeah, because the size, m equals 2, and n equals 3, equals 1. 2 and 1, right? 2 and 1. 2 and 1. So here, 1 is 2, 1 is 1. The minimum is 1, right? Yeah. Minimum is 1. Based on our notation, 1 comparison, and array size is adding together 3, right? Yeah. So 1 comparison, 3 array size. Oh, sorry, vertical bar. Okay. Yeah. I use vertical bar. Okay. Yeah, here. Okay. All right. Then here, merge. Okay. Merge based on our notation, 1 comparison, 2 array size. The merged array size 2. Okay. Yeah. Here, against that round 3. Yeah. We do against that round 3. So, sorry, 1 comparison because minimum is 1. Array size is 3. Okay? All right. Here, the minimum is 1. Array size is 2. Then, let's calculate the subtotal. Okay? The subtotal. The subtotal. 1 plus 1 plus 1 plus 1, 4 comparisons, right? Four comparisons. Okay? All right. Then, now against round 2, merge these two. This time we need to look at the array size. That's why you can see the array size number useful. Okay? 3 and 2. Yeah. Because this time when we do, you need to look at the 3 number and the 2 number. Okay? Yeah. Minimum is 2. Total size adding together 5. Okay? Yeah. So this round 2 bar 5. And merge these two, 2 bar 5. Right? Subtotal 4 comparisons. Okay? All right. Then the last round. Now the last round. Okay? 5, 10. The last round. Okay? 5 minimum, array size 10. Okay? So the subtotal, the last round. Last round. 5 comparison. Now you calculate total. Total. 2 plus 4 plus, 2 plus 4 plus 4 plus 5, 15. How about that? That's the best case. That's the best case. Yeah. Yeah. That's the best case. Yeah. Yeah. Although a little messy, but next slide, I show you the worst case. You know, you can see better. Yeah. Just formula different. Okay. The procedure the same. Just when we calculate the formula, use a different formula. Okay. So next one, I run this process again, but change the formula. Now, here for our question number 17, I still use n equals 10. Okay, 10 to show you. But this time, the worst case formula, m plus n minus 1. That formula. Every time when we merge, we use this formula. All right, so then let's run it. Okay, same as before. This time I have more space, so I can draw, larger diagram. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, the first split here, round 1 split. Okay, second here, round 2 split. Round 2 split. Third, round 3 split. Round 3 split. Round 3 split. Round 3 split. Okay? All right. Yeah. And because the last round, we just use one comparison to sort it. Okay? So one comparison to sort it. So we do not do split another round. Yeah. So this gives us subtotal 2 comparisons. Okay, 2 comparisons. Now, merge. Reverse. So, round 3 first. All right. This time, 2 and 1. Okay? Yeah. M equals 2, N equals 1, 2 plus 1 minus 1. That's 2. All right? So, 2 comparison, 3 elements. Okay? All right. So merge these 2 adjacent subarray. The total size 2, 2 minus 1. All right. 1 bar 2. Okay. Yeah. Here merge these 2 adjacent. All right. So 2 bar 3. Merge these 2 adjacent, 1 bar 2. Okay, all right. Subtotal, only count the number of comparisons. Subtotal, 2, 1, 2, 1. 6 comparisons. 6 comparisons. Okay, all right. Then, reverse the second round. Reverse round 2. This time, we use the size number. 3 plus 2, 5. 5 minus 1, that's 4. 4 bar 5. 4 bar 5. Okay, all right. Subtotal, 4 plus 4, 8 comparisons. All right, yeah, 8 comparisons. Then, the last round, use the 2 sides number 5, 5. 5 plus 5, 10. 10 minus 1, 9. Okay, so 9 size 10. The subtotal is 9. 9 comparisons. Okay, Then we calculate the total. Okay? 2 plus 6 plus 8 plus 9. 16 plus 9, 25, right? Or 10, 19, 25. Yeah. So here you can see the worst case, 25 comparisons. Previous one, best case, 15 comparisons. This one, 25 comparisons. That's the way you do it, okay? Yeah. When you work on these two questions, yeah, the number is different. Okay. The first one you do 8. Second one you do 12. Same process, same procedure. Okay. Yeah. All right? Yeah. Do not use formula. Do not, n log n. Do not use the n log n, okay? Asymptotic. We know asymptotic means not accurate, not exact, accurate formula. Here we want to have exact number, right? Yeah. Exact comparison number. Yeah. Here, 25, that's the exact comparison number. The previous one, 15, that's the exact comparison number. When you use n log n, it's not an integer, right? Usually it's not an integer. But every semester, there are some students just use n log n. That's wrong. That's wrong. Even no partial credit. Okay? If you use n log n, even no partial credit. Okay? Partial credit, if you know this formula, you can get partial credit. Okay? Yeah. If you know this formula, you can get 1 point partial credit. Because it's relevant, right? But your n log n is completely, it's irrelevant, okay? It's a wrong direction to go. So no partial credit. Yeah. All right, yeah, so that's these two questions. Yeah. Yeah. Any other questions? Yeah, so you can ask me. Yeah. Otherwise, yeah, I just follow the, plan today. Oh, you have a question? Yeah, yeah, 21.
For the array, when you're calculating do you use the entire array, or do you use what you're trying to search for? It's between 7 and 20th element.
Entire array. Yeah. Remember, in one of our previous video, I talk about that, entire array, okay? Yeah, I explained because we do not know that property. See, we treat that property as a hidden property. Yeah, between 7 and 20 something, yeah, that range, only we finish data processing, we look at the statistics, we know that, okay? But before we process all the search operations, we don't know it. If we don't know it, you cannot. So you cannot adapt your algorithm to that smaller range. Yeah. So use the whole array to build your binary tree, and then do the average. No, not denominator, as the binary tree. Denominator is still the number of elements in that range, 7 and, yeah. The denominator, yeah, because that's the number of searches we do, right? Yeah, so you average. What I mean is, because when you count, you build a binary tree, you need to count number of comparisons, right? 1 comparison, how many nodes? 2 comparisons, how many nodes? 3 comparisons, how many nodes? When you count those numbers, you use the whole array binary tree, okay? Not the partial array binary tree. Yeah, answer will be different. Yeah, that's the meaning. Yeah. Yeah. So this question, because so many students, many online students ask me this question. Yeah. I remember I talked about it, yeah, last week, right? Yeah, class. Yeah. Yeah. C2, part C2 video. Yeah, part C2 video I talk about. Part C1 video I talk about another hint. That phi, recurrence, remember? Recurrence relation, part of C1. I talk about recurrence. These two questions, most students ask me these two questions. Now, another two. So I talk about 4 questions in this assignment. Yeah. All right. Yeah. Next, let's move to our, my plan. Yeah. All right. R.1, selected questions of quiz 4. Yeah. I opened up the answers. Okay. Quiz 4, quiz 5. Now, if you go there, you can see the answers. Yeah. I open up answers. But here, I need to explain selected questions, relatively hard questions. Because if you look at answers, you may not understand. Yeah. So here, I explain why those answers. Question number 3, this phi one. Yes, this phi one. Yeah. Relatively harder. So, yeah, let me explain. Golden ratio expression, phi to the m. This expression can always be represented in the form of integer a phi plus b. Answer is true. Answer is true. Yeah. But here I want to show you why answer is true. Yeah. We use 2 basic properties. Actually, that 1. 1 equals phi squared minus phi. Yeah. Second one we do not use. Second one is the phi squared equals 1 plus phi. Here we just use the first one. Oh, sorry. Yeah. Actually, we use second one, not first one. All right. Use second one. We do degree reduction. All right. So we use this formula to do the degree reduction process to reduce the degree. Yeah. So let me show you how to do the degree reduction. Yeah. So here I just want to explain why it is correct. Okay, all right. We want to represent phi to the n. Yeah. Phi to the n, so here we assume, so here let's assume n greater or equal to 3. So we try to reduce, okay, all right. Yeah, actually greater or equal to 2, to do reduction. Yeah. Reduce below 2. There, we're done. Less than 2, it's 1, degree 1, okay, all right. So we write phi to the n minus 2 times phi squared. We can do that, right? We do multiplication. Yeah. All right. So then, phi to the n minus 2, phi squared, can we use the property here, replace it by 1 plus phi? 1 plus phi. Yeah. Then, do multiplication. Phi n minus 2 plus phi n minus 1. Here, can you see the degree is reduced by 1? The highest degree is n minus 1. Okay? So the degree reduced from n to n minus 1. Okay? All right. After that, can you do further reduction? So here, the highest is 1. Can we do further reduction another time, reduced by another 1? For example, phi n minus 3 times phi squared. Another round reduction. Yeah, right? So every time we can reduce degree by 1. Okay? Yeah. Every time when you have the highest degree term, you reduce degree by 1. Okay? All right. think about, eventually we will get degree 2, right? Degree 2, we do another reduction. So then finally we will get degree 1 polynomial. One polynomial. Because after we get degree 1 polynomial, we have to stop. Because we won't have phi square anymore. Whenever you see phi square, you can do reduction. So after we do all the reductions, then you cannot find phi squared. Okay? So we get degree 1 polynomial. Is the degree 1 polynomial just that a phi plus b? Integer coefficients. Because in our degree reduction, we always use integer coefficients, right? Yeah. We won't have, fractional number coefficients or integer coefficients. Yeah. So that's the, how you see it, okay? Yeah. It's a little abstract. So this kind of analysis. Yeah. So for this class, other than the computation questions, we may need to do some abstract analysis. Sometimes you need to do, a little higher level work. So abstract analysis, higher level of work, not concrete computation. Yeah. Yeah. So that's this question. Yeah. All right. Next one. Yeah, this one. Yeah. So first, the answer is no. We cannot use this way. Yeah. Because remember when we calculate, so the binary tree, because when we calculate the average case efficiency, we calculate the average number of comparisons for the top level, one comparison, right? So the next level, 2 comparisons. Then this level, 3 comparisons. This level, 4 comparisons. But when you do average, you can see the number of nodes at each comparison, the number different, right? So think about, if the same number, then you can do that, right? Think about the same level, okay? So suppose S comparisons, next level also S all level you have S comparisons, then you can use this way, right? Yeah, top level, yeah. But here, each level, different levels, the number of comparisons different. Then you cannot use that, 2 numbers adding together divided by 2. You cannot. Okay? Yeah. So you have to do the weighted average. Yeah. So this case, you have to do weighted average. And for the weighted average, you need to choose appropriate weights. Yeah. Different level, the weights is different. Okay? The weights is different. Yeah. Yeah. So then you choose the number of nodes, that's the weight. Okay? Number of nodes. Number of nodes over the weight. So here you may ask me, what's the meaning of weight? Each weight, so a weight. The meaning of a weight here. A weight for a level, yeah, because each weight corresponds to a level, okay? For a level equals, so it's a fraction. Fraction. The new denominator is total. number of total nodes, okay? Yeah. Number, total nodes, that number, okay? All right. Then, the numerator, number of nodes, in this level. Okay? That's the meaning of weight. So you take a weighted average using this weight definition. That's the right way to calculate average case efficiency. Okay? Yeah. But you can see the weights for all levels are different. Okay? Yeah. So that's the, this question. Yeah. Why not correct? Yeah. All right. Number nine. Given 5-element array with distinct elements, we want to sort this array with an optimal solution. How many comparisons do we need for the worst case? 7. We did it in class, right? Yeah, we did it in class. Yeah. Yeah. So you can find in our notes, we find the sorting algorithm using 7 comparisons to sort it. Yeah, I drew the diagram. Okay, so if you find the notes, so you can see my annotation in the diagram. Yeah, 7. But the question is, how do you know this 7 is optimal? Yeah, we know we get a solution with 7 comparisons. But the question is, how do you know this 7 comparison is optimal? That means no other people that can sort 5-element array with 6 comparisons. Yeah. No, even in future after 500 years, nobody can sort it with 6 comparisons. That means it's optimal. Okay? Yeah. Remember, use last class the formula. Yeah. So the formula, lower bound formula. Yeah. Floor function log base 2 of n factorial. Yeah. Because this is the lower bound. Lower bound means nobody can do better than this number. If we find the lower bound equals 7, then nobody can do better than 7. That means this one is optimal. That logic, simple logic. Okay, all right, so let's just calculate the lower bound. Lower bound, log base 2 of 5 factorial. Okay, 5 factorial, that's 120, right? Equals 7. Because 2 to the 7th equals 128. 2 to the 6th, 64.
Sorry, you were saying floor function?
Oh, ceiling function. Yeah.
Floor or
Ceiling, yeah. So I got it wrong. So I said floor function, right? Yeah, I got it wrong. Yeah, correct. Yeah. So yeah, thank you for correcting me. Yeah. Yeah. Ceiling function, not floor function. Okay, ceiling function. Yeah. Yeah. So I got confused. Yeah. Ceiling function. Yeah. All right. Yeah. Number 9. Yeah. Yeah. R.2, selected questions of quiz 5. Yeah. When we apply the quicksort, number 4, on an array that has been already sorted, ascending order, okay? Ascending order. We will get best case false. We will get the worst case, not the best case. Okay? So here, yeah, we will get the worst case. Reason, because the data is not balanced. Okay? The pivot, when we select pivot, So, or you use randomization, yeah, you can do much better. Yeah. But if you do not do randomization, so it's the worst case. Yeah. All right. Number 6, yeah, this one, similar question. This time, 1 over phi to the n. Yeah. Answer is yes. Yeah. Even 1 over, we can still represent that expression as a phi plus b. Yeah. Yeah. All right, so here, let me show you. Yeah. Let me show you. Okay. Yeah. Still use these two properties. All right. Yeah. This time, reciprocal. Yeah. There is an easy way to do it. Okay, all right. First, let's just do 1 over phi. How about that? 1 over phi. Okay? 1 over phi, we apply first property, phi squared minus phi over phi. We can do cancellation, so we get phi minus 1. So that's a linear polynomial. Okay? All right. With that, now, 1 over phi to the n, can you write phi minus 1 to the nth? Phi minus 1 to the nth, that's a polynomial of degree n, right? Polynomial degree n, by our previous result, can we do degree reduction to get a linear polynomial? Right? Yeah. So here, previous result. Okay? We did it. We just did it. Okay? And the degree reduction. So we can get a linear polynomial. Okay? Linear polynomial. Yeah. So that's, a phi plus b, yeah. Integer coefficients. Yeah. Yeah, because so this polynomial with integer coefficients, right? Yeah. So the polynomial, you do the reduction with integer coefficients. Okay? Integer coefficients. Yeah. So then, because when we use the properties, we always use the integer coefficients. Yeah. All right. Yeah. So here you can see. Yeah. Yeah. All right. So so this kind of analysis skills. Yeah. So you need to, try to improve, yeah, to be able to do this kind of abstract analysis. Yeah. All right. Next question. Yeah. So this one, yeah. So this one, yes. Some student asked me this one. Here, my recommendation, you draw a diagram to see better. Yeah. Yes. Some students just look at the formula, couldn't figure out. Yeah. Yeah, because, I try to understand the psychology of those students, because they feel binary search, the case could be very complicated. So how do you know which case? Yeah. Although we know average case close to the worst case, right? Yeah, distance less than 1. Yeah. So we know W minus A, yeah, I remember I give you this number. We know it's positive. This number less than 1. We have that result. Less than 1. Yeah. All right, so here, let's draw a diagram. Okay? All right. This 1 is the best case. Okay. W, worst case. Okay? All right. So then they're averaged somewhere in the middle. So this is B plus W over 2. And we know our average case is very close to the worst case, A. And the distance less than 1. The distance less than 1. Now you look at, you compare this point and the midpoint, which one is larger? Right? So from the diagram, you can see which one is larger. Yeah. Right? Yeah. So C is correct. Yeah. Just draw a diagram. Okay? Yeah. But you need to know this. Yeah. So when you draw a diagram, you need to know this result. A is very close to W. Yeah. Okay. All right. Yeah. So then, R upon 3, examples for heap sort. Yeah. Because I couldn't, we do not have time to practice this topic. Yeah. So here I give you some sample questions. So if in the final, if you see questions similar to these sample questions, okay, you just study, prepare for the final. Okay. So here I select 4 questions. The first one, given a max heap whose values correspond to the array indices from 1 through n. Yeah, no 0. Yeah, so here I already, yeah, because otherwise many students ask me, so 0 or 1, yeah. So first element at index 1, 2. All right. The last element at index n. Yeah. Now, what is the smallest possible? Yeah, remember here the max heap. Yeah. The structure is max heap. Okay. Yeah. So then we look at the smallest possible index for what? For a node with height 2 of the heap. Height 2 of the heap. Okay, all right. Yeah. So here, so remember the formula. Yeah. So we did some formula. Okay. Yeah. Yeah. But here we will see that formula easily. In this diagram, we will see that formula easily. Okay. All right. Yeah. So here to answer the question, height 2. Let's start from height, so here, let's start from height 0, then height 1, then height 2. Yeah. All right, so height 0, the leaves, those leaves, yeah, remember the leaves, the range of the leaves, the range. Okay, so here, formula for the range, leaves, that is floor function n over 2 plus 1, right? This is the range of the leaves. Leaves. Yeah. Leaves. Okay? All right. Then, range of height 1 nodes. Range of height 1 nodes. The upper bound should be, yeah, next to the upper bound is n over 2 floor function. Yeah. The lower bound, n over 4 plus 1. So this range is the height 1 node. Height 1 nodes. Okay? That range. All right. Yeah. All right. Then, height 2 range. The nodes height 2 range. N over 4. This time floor function. Yeah. flow function. All right. Then this side, n over 8 flow function plus 1. That range, this range, okay? That's the high 2 range. High 2 nodes. All the high 2 nodes. Okay? Yeah. All right. So now from the diagram, we see that's the range. Okay? The range, the lower bound, n over a plus 1, upper bound, n over 4. Okay? All right. Now you tell me, what is the smallest possible index? Yeah. What is the smallest possible index for node with high 2? What's the smallest possible index in this range? This number, right? Yeah. This number is the smallest possible index. Okay? Answer. Yeah.
Is that n over 8?
Yes, n over 8. Flow function n over 8. Flow function n over 8. Plus 1. Okay? Plus 1. Yeah. All right. So this diagram, yeah, to answer these heap questions, this diagram is important. Okay? So if you understand this diagram, then you can solve many questions. Okay? Many similar questions. Yeah, this diagram. All right. Next one. Given a heap with n nodes, if we know that there are 40 leaves in this heap, the condition, we know 40 leaves in this heap. What are the possible values you can take for n? Number of leaves. What's the formula? Number of leaves. Yeah, so here. Number of leaves. Ceiling function n over 2. This number equals 40. Yeah. N over 2, ceiling function. That's the formula for the number of leaves. And we know it's 40. Now, what are the possible values for n? Yeah. Yeah. To solve this one, yeah, because, yeah, right, 80, 81, good. Yeah. 80, 81. Yeah. Yeah. So when you look at this, see this question, so here, you can do it in this way. Yeah, because many people, they may not know how to deal with the ceiling function. Ceiling function. Yes. Yeah. All right. Although you may have different ways to do ceiling function, but there is one simple way. Yeah. So here I can recommend a relatively simple way for you. You know, for similar questions, you can try this way. Okay. All right. Yeah. First, the first step is the approximation step. Okay. Approximation step, that means you allow some small error, okay? You know, small error, you just want to get close. You want to find an n close to the true answer. You want to get there as fast as possible, okay? All right. When you do approximation, let's just remove the ceiling function. Let's look at this equation. This is easy to solve. And we know it's an approximation. So, you know, we can fix that small little error, okay? All right. So, yeah. Then, you know, n equals 80. All right? Yeah. Second, test a few numbers around n, around 80, around, yeah, because nearby, okay? Do some testing around 80, okay? Yeah. So you can try 80, 81 works or not, you know, higher 81 works or not, yeah, plug in, 81 works. Yeah, yeah, 80, oh sorry, 81 doesn't work, good, yeah, good point. 81 doesn't work, then do not go up, okay? 81 doesn't work, do not go up, going down, okay? Yeah. So 80 works, then 70, because 80 works, 79. 79 works or not, ceiling function works, okay? Yeah. 78 works or not, doesn't work, 39, so you stop, okay? Yeah. You know, the solution, because here, upper, you know, doesn't work. Yeah. So you stop. Lower, here, you know, doesn't work. Stop, okay? In the middle, these two numbers, it works. Yeah. So this method I recommend, okay? Recommend, yeah. Because our next question, we'll have a similar one. Yeah. So let's use this approach. Let's solve the next question. Next question. Yeah. All right. Number 3. Number 3. Yeah. All right. We have enough time. Yeah. The last 2 questions, so we have enough time. Yeah. Given a heap with n nodes, if we know that there are 60 nodes with height 1, 60 nodes with height 1 in this heap, what is the minimum, what is the possible values you can take for n? Similar to the previous one, but this time, height 1 nodes. Yeah, let's use the same method to solve, okay? All right, first, because we need to represent the number of height, so here, the question, you need to know the formula, number of height 1 nodes. Okay, all right. N over 2 floor function minus N over 4 floor function, right? Can you see that? Can you see that? Yeah. So if you cannot see, yeah, so here, first, this formula appears in our notes, okay? So that's one. Second, even if you do not look at the notes, here, let me point to the, you know, previous, this slide. You look at the range here. Height 1 nodes, this is the range. You use the upper bound. What's the upper bound? Upper bound n over 2 minus 1 less than the lower bound, right? Yep. Because you cannot minus lower bound. Minus lower bound, you exclude the lower bound, right? You don't want to exclude the lower bound. So you minus 1 less than the lower bound. So that is n over 4. Okay? So that's the number of height 1 nodes. Okay? The formula. From diagram, you can also see it. Okay? From this diagram, you can see it. Even if, you know, you couldn't find, you can find formula from notes. Yeah. If you do not bother to, you know, look up in the notes, yeah, from this diagram, you can see it. Okay? All right. Then, let's use this formula to solve our example number 3. Yeah, here. Yeah. All right. Example number 3, this time this formula, all right, yeah, harder than our previous question. So the first step, approximation, that should be easy, right? Approximation, that should be easy, okay? Yeah. Remove the floor function. just, n over 2 minus n over 4 equals n over 4 equals 60, right? Yeah. N over 4 equals 60. To find n, that's easy, right? 240, right? 240, the first step. The answer should be around this 240, okay? Answer should be around 240, okay? All right, yeah. Testing around 240, okay? All right. Let's try 241. Good or not, okay? 201. Good, right? Yeah, yeah. Right. 120 minus 60. Yeah, all right. So it's good, 241. It's good, okay? Let's test 242. Yeah. So here, 241. Good. Yeah. Then let's try 242. Yeah. 242, yeah. 1 to 1. 1 to 1 minus 60. One more. So we should stop. Okay? All right. Then 240, we know it's okay. It's good. Yeah. Then 239. Flow function, 119, right? Yeah, sorry, because 120 less minus 1, 119. 119 minus 59, right? Is it 59? Yeah, 59. That's 60. It's good. Okay? Then test 138. 138, also 119, right? 119 minus 50, also 59, right? Yeah, also good, 59. Also good, okay? Yeah. Here you can see, you see 4 answers. The denominator is 4. That should be there. Yeah. So, because the previous one, denominator 2, we have two correct answers. Here, denominator 4, we have 4 correct answers, right? Yeah. So here, 4. Although you can test, you can check, yeah, but it won't work. Okay. Yeah. It won't work. Yeah. So you can check 237. 237, 118, right? 118. Yeah. But still 59, right? Yeah. So it won't work. Yeah. But after you get 4 answers, that's all you have. Yeah. This method, how about that? This method. Okay? Yeah. Approximation. Yeah. Final one, So you quickly locate that spot. Very close to the true answer. But yeah. Then look at, upper a few, lower a few, adjacent. Yeah. This way you can solve. Okay. Last question today. Last question today. Okay. All right. Given a heap with n nodes, if we know that there are 100 longest paths from the root, what is the smallest number for n? Yeah, this is a little hard. So first, let's draw a typical heap, the structure. A typical heap structure. Right? Yeah. So then we have many levels going down, right? Yeah. Then at the bottom level, we know a heap is a near complete binary tree, this structure. near complete binary tree. Near complete binary tree. Okay, all right. That means only the bottom level may not be full. All the other levels must be full. Okay? All the other levels must be full. Okay? All right. Yeah. So then, the longest path, what are longest path? Longest path from the root to, to these nodes. Yeah. The leaf nodes, but with the, that's the longest path. Yeah. So not to these leaf nodes. There are a few leaf nodes here, but that's shorter. The path shorter. Yeah. All right. So here we know 100 nodes like that. All right. Now to solve it, we need to find a math representation to solve. All right. Yeah. All right. Because think about if we cut off the lowest level, if we cut off, okay, then this is a complete binary tree, right? Complete. Complete binary tree, we know the number of nodes, 2 to the k minus 1, right? Complete binary tree, the number of nodes, 2 to the k minus 1. Okay? All right. So now, the total nodes is n. Yeah. N. Yeah. So how many nodes at the lowest level? How many number of, so here, number of longest. So we need to remove these nodes from the total nodes. So n minus 2 to the k minus 1 equals 100. Yeah. Equals 100. Yeah. Yeah. But this number, yeah. So here, okay, all right. This number. All right. And n less than 2 to the k plus 1 minus 1. Yeah. Because if the bottom level complete, less than equal to. Because the bottom level could be full, right? The bottom level could be full. Longest. Yeah. So we have the condition. This condition and that condition. Okay, yeah, that condition. All right, yeah. So now, with this condition, can you find the answer? Yeah, so here, n greater or equal to 100 plus that number, so that is 99 plus 2 to the k, less than equal to 2 to the k plus 1 minus 1. Okay? So you have this inequality. All right. Then you skip that n. Okay? So you have that 2 to the k. When you skip that n, so 100 less than equal to 2 to the k. Right? Can you see that? 100 less than 2 to the k. So the smallest k, so here, so first k, the first k is 7, right? 2 to the 7th, greater than 100. The first k is 7th. Yeah. So let's try 7th. When k equals 7, n should be equal to 100 plus 127, right? 227. Is 207 less than or equal to, you check this inequality, okay? 255. Yes, right? So 7 is okay. Yeah. So n equals 227. You check it. Okay. But you may check k equals 8. You see if it works. If k equals 8, then n equals 100 plus 255. That's 355. Then you check, is it less than 500? Yes, yeah, definitely less than that. Oh, yeah. So here, you don't need to check. Remember, we find the smallest number for n. We'll find smallest number for n. Because larger than you can always get, right? So we want smallest number for n. Smallest, that's 227. When k equals 7. K equals 7, you plug in, you get smallest number for n. Yeah. Because larger, you can always get larger. Okay? You can always get larger. Yeah. Question? Yeah, from this, so you feel okay with this inequality, right? Do you feel okay with that inequality? Because coming from, yeah. So actually this is equality. This is equality, okay? That is, yeah, because when the bottom is full, this number, when the bottom is full, right? Complete, whole complete. But we know, so that n should be in that level, right? So n cannot be more than that. Yeah. So that's the lowest level full is the number of nodes this many. Okay? Yeah. So that's why we have that. After we do simplification, we get this inequality: 100 less than or equal to 2 to the k. So the minimum k 7. How about that? Yeah. This inequality must be true. This inequality must be true. So 7. 6, no, not true. 64, not true. Not whole. Okay? Yeah. So from these inequalities, so you need to if you understand this condition, then you're fine.
Where did the original 255 from?
255.
N equals 100 plus 1.
Yeah, right. 2 to the 7 plus 1 minus 1. Oh, yeah. 2 to the 8th, 256. 256 minus 1, 255. 8 plus 1. 8 plus 1. Yeah. Yeah. All right. This is the hardest one. Yeah. Yeah. If I give you a not, I'm not sure. All right. Yeah. Try to understand. Yeah. If you have a hard question, this will be the hardest. Okay. If there is a hard one, this will be the hardest. But you have this example, right? Yeah. So you can study this example. Okay. All right. Did I say anything about I will leave last 5 questions online? Yeah, but on syllabus I said that, right? Yeah. Yeah, on syllabus I said that. So the last 5 questions, so you have chance. So after Monday, I give you up to Thursday. Yeah, on syllabus, I give you a little more than 3 days to complete. So you can submit last 5 questions on Thursday. Yeah, correct. Yeah. 2 lowest quizzes, drop it.